On October 12, 2025, a permit was quietly filed in Fremont, California to convert a Tesla car factory into a humanoid robot production line. That document was never supposed to draw attention, but what it connects to is far larger than one factory: a $25 billion chip fabrication plant, Pentagon AI contracts, satellite surveillance, and drone swarm programs, all feeding one network. The global robotics industry ships roughly 500,000 units a year. Tesla's target is 10 million. And what no one is prepared to answer is what happens when a single ecosystem controls the robots, the rockets, the AI, and the chips. Permit number 2025 FRE 1123, filed on October 12, 2025, lists Robotics Systems Inc. as the primary contractor for a sweeping alteration inside Tesla's Fremont facility. The language in the permit is clinical: removal of 1.2 million square feet of vehicle assembly tooling, installation of modular robotic cell frames, and reconfiguration of the main floor for non-automotive manufacturing. The document does not mention Optimus by name, but the scope, stripping out Model S and Model X lines and retooling for high-mix multi-stage assembly, matches Tesla's own public statements about repurposing the plant for robot production. The permit's technical attachments detail the removal of paint booths, chassis alignment stations, and the introduction of 6-meter-wide modular cells, a footprint that aligns with the 2025 investor deck's illustrations of the Optimus line. The contractor, Robotics Systems Inc., appears in municipal records as a specialist in high-density automation installations, with previous contracts tied to aerospace and semiconductor facilities. The city's own stamp on the permit signals official approval for a transformation of the factory's core purpose. In the world of industrial manufacturing, permits like this are rare in both scale and intent. They serve as the paper trail for a shift from cars to robots, anchoring speculation in verifiable documentation. What remains unaddressed in the permit is the puzzle of space. The Model S and Model X lines, 1.2 million square feet, fall short of the theoretical requirement for 1 million robots per year, raising questions about cell design, shift patterns, and whether even this scale of retooling can meet the targets Tesla has set. The permit is not a press release or a forked stimulus. It is an official, signed order to erase the past and build something entirely new. Giga Texas exists on a different scale, an ambition that dwarfs even the radical transformation underway in Fremont. In November 2025, Tesla announced plans for a dedicated robot factory outside Austin with a target that stretches the boundaries of industrial precedent: 10 million Optimus units per year by 2027. That number is not just aggressive, it is almost 20 times the current global output of all industrial robots combined. According to the International Federation of Robotics, the worldwide market shipped roughly 500,000 units last year, across every manufacturer and every continent. Tesla's planners in Texas are not just aiming to lead the market, they are trying to redefine it, building an ecosystem where the output of a single site would eclipse the rest of the world put together. The renderings released in the 2025 investor deck show a 5 million square foot expansion, with 4 production corridors and nearly 15,000 modular assembly cells. The company's stated goal is to reach full output in less than 2 years, an acceleration that would require a supply chain, energy footprint, and logistics network on the scale of a national infrastructure project. The comparison is stark, where Fremont's conversion raises questions about fitting 1 million robots into a car plant. Giga Texas is designed from the ground up for a scale that industrial robotics has never seen. The stated target is not just an engineering challenge, it is a bet that Tesla can bend the global market to its will, turning a speculative project into the main event. Every element, from the construction budget to the assembly line layout, signals a willingness to outspend and outbuild every competitor. The question is not just whether the technology is ready, but whether the world is. Floor planners inside Fremont face a problem that is almost mathematical in its bluntness. The assembly cell, as defined in Tesla's own technical attachments, consumes a 6-meter-wide footprint, about 256 square feet per module, to reach the stated target of 1 million robots per year. Benchmarked against high-mix automation standards, the factory would need roughly 7,200 concurrent cells. That is a theoretical minimum, assuming 2 full shifts and a cell cycle time of just over half an hour per robot. When multiplied out, the required area reaches 1.84 million square feet. The available floor space in the repurposed Model S X Hall is 1.2 million square feet. The gap is not a rounding error. It is over 500,000 square feet missing from the equation. Every cell, every aisle, every inch of staging and storage now becomes a constraint. Industrial benchmarks from Boston Dynamics and Amazon Robotics show that even with advanced multi-stage flow and shared tooling, the compression ratio Tesla faces is unprecedented. Planners are left to consider pushing shift counts to 3, squeezing cycle times further, or stacking operations vertically. Each option introduces new layers of complexity and risk. The numbers leave no room for optimism without radical breakthroughs in hardware density or assembly speed. Until those are proven, the physical envelope of the factory itself stands as the first hard limit on the scale of the Optimus project. Gen 3 introduces a mechanical leap that stands out even in the crowded field of advanced robotics. Each hand, driven by a tendon system, packs 25 actuators, bringing the total to 50 for both arms. This is not just a number on a spec sheet. The arrangement allows for 22 degrees of freedom, giving the robot the ability to move each finger, thumb, and wrist with a level of independence that approaches the human hand. The actuators themselves are compact brushless motors stacked inside the forearm, linked to high-strength synthetic tendons that transmit force with minimal slack. This design keeps the hand slim, avoiding the bulk that plagues most dexterous robots. Close-up footage from Tesla's engineering demo shows the hand flexing, rotating, and even threading a needle, a benchmark that demands not just power, but fine control. Internal sensors track every joint's position in real time, feeding data back to the AI-5 chip, which runs a fast parallel control loop. The result is a system that can grip a delicate object, adjust force on the fly, and recover from slips or errors in milliseconds. Musk himself described the Gen 3 hand as sublime. He predicted that once perfected, it will not even seem like a robot. But the leap in actuator density comes with new questions. Packing so much hardware into a small space raises concerns about heat, energy draw, and long-term reliability, issues that do not show up in a demo, but become critical at scale. The tendon system, while elegant, faces wear and tensioning challenges that have yet to be solved for millions of cycles. For Tesla, the bet is clear. If this architecture can be made to work, it unlocks a pathway to mass production and tasks far beyond simple pick and place. The risk is that without robust solutions to energy and durability, the very hardware that promises a breakthrough could become the next bottleneck. Tesla's financial disclosures for 2026 reveal the scale of commitment behind the Optimus project. In the fourth quarter of 2025 earnings slide deck, a single number stands out: $20 billion in capital expenditures allocated for the coming year. The figure is not spread across a decade or split among multiple ventures. It is concentrated, immediate, and dwarfs the company's previous annual investments. The slide places optimized manufacturing and AI-driven robotics at the center of the plan, making clear that this is not a side bet. Yet the balance sheet tells a more complicated story. Free cash flow for the same period is negative $5.19 billion, a swing deep into the red that signals how much Tesla is willing to burn through to secure a lead in robotics. The company's finance team, usually known for cautious optimism, now presents a forecast that hinges on future volume rather than present returns. The numbers are not just abstract projections. They translate into construction contracts, equipment orders, and rapid expansion of chip manufacturing and battery lines. Investor language in the 2025 earnings deck is blunt. CapEx will exceed $20 billion in fiscal year 2026, primarily for robotics and AI infrastructure. There is no attempt to soften the risk. The bet is that pouring tens of billions into hardware before the robot can perform reliably in the field will create an unassailable lead when the technology catches up. Every dollar spent now is a wager that the convergence of AI, robotics, and manufacturing scale will pay off before the cash runs dry. The financial surge is not a footnote. It is the backbone of Tesla's industrial transformation, and it sets the stage for even larger investments in AI and semiconductor production that follow. On January 16, 2026, Tesla filed a notice with the Securities and Exchange Commission confirming a $2 billion transfer from its own accounts to xAI, Elon Musk's artificial intelligence company. The filing, buried among routine disclosures, details a direct cash injection, no convertible debt, no equity swap, just a straight transfer of funds. The official reason given is strategic alignment of AI and robotics initiatives. But the timing and amount stand out against Tesla's own capital needs. The $2 billion sum is nearly a tenth of the company's annual capital expenditure plan for 2026, and it arrives at a moment when Tesla's free cash flow is already deep in negative territory. The transfer cements the relationship between Tesla's hardware ambitions and xAI's software roadmap. Corporate officers from both firms signed the filing, including Tesla Chief Financial Officer Vaibhav Taneja and xAI's Chief Executive. The language is careful but pointed. The investment is earmarked for joint development of large-scale AI models and real-time robotics control systems. The filing's existence is more than a financial footnote. It ties Tesla's physical build-out, including factories, robots, and semiconductors, to a software entity with its own defense and data contracts. The money does not flow to a supplier or an outside partner, but to an AI arm that shares ownership, leadership, and long-term incentives with Tesla itself. This move welds the company's hardware spending to the fate of its AI ecosystem, setting up a structure where cash and control circulate inside the same network. The implications for future military and government contracts are left unstated, but the architecture is now in place. A $25 billion line item appears deep in Tesla's 2026 capital plan, labeled simply as Terafab, the Texas Semiconductor Hub. The figure is staggering. It is more than the entire construction budget for Giga Texas itself. But the logic behind it is simple. Scale at this level demands a chip supply that no outside vendor can guarantee. Terafab is not a generic foundry. Internal engineering briefs describe a facility designed to produce custom system-on-chip modules for every part of the Musk stack: robotic controllers, artificial intelligence accelerators, satellite modems, and vehicle autopilot processors on a single, vertically integrated line. The plant's design calls for extreme ultraviolet lithography tools, silicon carbide furnaces, and multi-product wafer lines capable of shifting from automotive-grade logic to high-bandwidth artificial intelligence cores without a full retool. The economics of this approach are as aggressive as the technology. By centralizing chip production, Tesla can amortize the $25 billion investment across robots, cars, satellites, and defense projects. The same wafer that powers an Optimus hand could, in theory, drive a Starshield communications payload or a Grok inference server. This is not just about cost per chip. It is about controlling the physical layer that connects every part of the networked empire, removing the risk of external supply shocks, embargoes, or intellectual property leaks. Engineers inside Terafab work in cross-disciplinary teams, blending robotics, artificial intelligence, and semiconductor design under one roof. The result is a hardware backbone that glues together the ambitions of Tesla, SpaceX, and xAI, creating a closed loop where software, hardware, and data never leave the ecosystem. The bet is enormous. Billions spent before the robots can reliably perform useful work, all on the assumption that vertical integration will pay off when the scale tips from prototype to ubiquity. A $200 million contract awarded to xAI by the Department of Defense appears in a handful of press briefings and news reports from early 2026. The official language describes a multi-year agreement to integrate Grok, xAI's large language model, into classified Pentagon networks. The contract text is not public, but statements from the Joint Artificial Intelligence Center reference secure AI hosting, real-time threat analysis, and natural language search across sensitive data streams. CBS News and Defense One both confirm the award amount and the scope. Grok is tasked with parsing intelligence feeds, assisting analysts, and supporting decision-making in secure environments. Axios adds that xAI is the only vendor providing a language model-based engine for this mission. The contract registry excerpt, while redacted, lists xAI as the principal recipient and assigns the $200 million figure to AI-enabled decision support for classified operations. Pentagon officials describe the system as a bridge between human analysts and vast siloed datasets, offering instant cross-correlation of signals, imagery, and communications intercepts. The architecture requires Grok to operate inside Department of Defense-approved cloud environments, isolated from the public internet, with ongoing fine-tuning against classified corpora. This is not a research pilot. The statement of work mandates operational deployment, continuous model updates, and integration with drone swarm control interfaces. The language is blunt about the end use, rapid battlefield intelligence, autonomous targeting, and real-time command support. In effect, Grok becomes a software layer in the Pentagon's digital nervous system. The contract does not mention Optimus or robotics directly, but the linkage is implicit. Algorithms built for one Musk company now underpin the decision cycles of national security. The boundary between commercial AI and military infrastructure is no longer theoretical. It is a $200 million line item, awarded, signed, and underway. The Department of Defense issued a contest specification on December 18, 2025 for a voice-commandable drone swarm, a networked weapon system able to receive spoken orders, split tasks across dozens of units, and adapt in real time to changing battlefields. The requirements, published by the Pentagon's Procurement Office, call for drones that can coordinate flight paths, sensor sweeps, and even targeting routines, with latency under 80 milliseconds. The contest is not limited to traditional defense contractors. The language explicitly invites proposals that fuse large language models with distributed hardware, AI that can translate voice instructions into synchronized action across a mesh of autonomous vehicles. The operational path is clear. Language models like Grok, already embedded in classified DoD networks, are now being paired with physical force multipliers. Instead of a human operator flying one drone at a time, the system listens, interprets, and issues commands to a swarm, each unit updating its path based on real-time feedback from the others. The contest specification demands that the swarm remain operational even if individual drones are jammed or destroyed, requiring fully decentralized control and secure low-latency communications. The architecture mirrors advances in Tesla's own vehicle and robotics platforms, edge compute, mesh networking, and AI-driven autonomy, all scaled to military requirements. This is not just an experiment in software. The Pentagon's documentation ties the performance of AI models directly to the physical effectiveness of autonomous systems in the field. The implication is unambiguous. Whoever controls the language model, the chip supply, and the communication backbone will control the next generation of networked weapons. The contest closes with a warning. Finalists must demonstrate swarms that can operate over satellite links, bridging terrestrial and space-based command layers. The convergence of AI, robotics, and secure space communications is no longer theoretical. It is written into the operational requirements of the world's largest defense buyer. SpaceX's Starshield program surfaced in defense contracting circles with a reported $1.8 billion deal attributed to the National Reconnaissance Office. The figure circulates in industry briefings and secondary sources, but no public contract number or official award notice has entered the federal procurement record. Starshield's stated mission is to provide secure orbital surveillance and communications, leveraging SpaceX's rapid satellite deployment and custom payload integration. The program's scope, as described in procurement summaries, includes a classified constellation designed for persistent global coverage, encrypted downlinks, and rapid tasking by U.S. intelligence agencies. If accurate, the contract value places Starshield among the most expensive private satellite initiatives ever attempted. SpaceX's program leads have shifted from launch services to end-to-end orbital systems, offering not just rockets but the satellites, ground stations, and network management required for real-time reconnaissance. The privatization of such a critical layer of national security infrastructure raises questions about oversight, data access, and the increasing dependence of government agencies on a single commercial provider. In the absence of public documentation, the true extent of Starshield's capabilities and the leverage it gives its operator remain shrouded, even as its budget signals a profound shift in the balance of orbital power. A civilian radio hobbyist scanning the 2025 to 2110 MHz band stumbles onto a digital downlink that does not match any known public satellite registry. The signal, pulsing in short encrypted bursts, appears at regular intervals over North America, always coinciding with overhead passes of a classified satellite cluster. By October 2025, the anomaly draws enough attention that NPR runs a brief segment. Unknown transmissions, possibly from a commercial satellite constellation, are saturating a protected slice of spectrum usually reserved for government and research use. The story notes the absence of any FCC filings or international coordination, raising questions about who authorized the signals and what data is being sent. The hobbyist, a retired engineer from British Columbia, posts logs and spectrograms online, prompting a flurry of amateur analysis but no official response. The incident exposes a blind spot in regulatory oversight, a system where private satellite operators can beam high-powered, encrypted data over civilian airspace with little external scrutiny. In a world increasingly reliant on proprietary orbital infrastructure, the question is not just what these signals carry, but who gets to decide where the boundaries of accountability lie. SpaceX now holds $22 billion in active government contracts, a sum that binds national security infrastructure to a single commercial supplier. In the same breath, Elon Musk claims that Optimus will end poverty, while Tesla's own disclosures confirm the loss of 55,000 jobs in 2025 as factory lines convert from human labor to automation. The rhetoric of self-replicating robots, von Neumann machines, collides with the reality that no Optimus unit can yet assemble another unit, or even itself. Robotics pioneer Rodney Brooks points out the gap. The promise of a universal worker remains an aspiration, not a product. The system is scaling faster than its core technology can deliver, and the world's largest industrial gamble is already reshaping the workforce before the machines are truly ready. Today, the boundaries between robotics, AI, defense, and infrastructure blur at a pace regulators can't match. Tesla's vertically integrated empire is no longer hypothetical. It is being built despite the robot's current limitations. As factories shift to machines that won't even seem like robots, the question isn't just what technology can do, but who controls it when everything connects. Power, not progress, may be the legacy. What do you think? Progress or peril?